Howdy. This is going to be your first of two lectures on frictional forces. And I want to just remind you of what we saw today in class. What we saw, in a sort of idealized sense, was that when we started applying force to it, then the force of friction grew. I'm going to label the force of friction with a little f right here. And it grew until it hit a certain point, and then it dropped off and kind of did this. And at the same time, we saw that the velocity basically stayed zero, like here, until this point, and then all of a sudden the velocity sort of climbed and then did whatever it did. So there's our velocity, like that. Now, we also observed that the frictional force increased as the amount of weight increased. So our setup was that we had our 2x6 with books on top of it that I'm going to represent like this. And we had a weight pulling down, and of course we have a normal force pushing up from the floor. And we had the force from the force sensor going this way, and then we had a frictional force dragging back. If we were to do this experiment more carefully, what we would discover is this: the following things about friction. The first is that it's clear from the diagram there are two types of friction. The first type of friction applies when the velocity is going to be zero, and we're going to call that static. Of course, the word static is the Latin word for standing. So this is the type of friction that is going to apply when the velocity is equal to zero. And there's going to be a second type of friction that is kinetic, from the Latin word for moving, when the velocity of our object is not zero, when it's moving. So we have static friction and we have kinetic friction. Let me fix my handwriting. And what can we say about these two types of friction? Well, let me make a nice little chart right here. I lost my K. Huh. Wow. There we go. Okay, so we have static and kinetic friction. And the static friction, I want you to notice, has the ability to increase until it hits a max point. Right there. So we could say that the static type of friction, F sub s, is going to be less than or equal to some maximum value. Whereas it looks as if our kinetic friction is a nice constant value. Then the second thing that we're going to find, if we can investigate this carefully, is that the maximum value of the static friction and the value of the kinetic friction are proportional, not quite to the weight, but to the normal force. That's going to be the key that causes the frictional force to act. Remember how in class I had you take your two hands and push them together to feel the normal force? I'd like for you to do that at this time. This time I'd like for you to try to rub them together just a little bit. And you can see that if you're not pushing very hard, you can rub your hands together. But if you push your hands together very hard, it becomes impossible to move them. They're locked in place. And that is the effect of friction. The force that is keeping your hands from moving past each other is the force of friction, and it's caused by the normal force there. And so because both of these are proportional to the normal force, what we're going to do is to write them as a constant times the normal force. And it turns out that the constant that is involved depends upon the two surfaces that are in contact. A rubber tire on a dry road will have one constant, and a let's say, an ice skate on a pond, frozen pond, is going to have a very different, much lower constant. We're going to assign a symbol for this constant, and that is going to be mu sub k for the kinetic friction, and it's going to be mu sub s for the static friction. And this mu sub k and that mu sub s are both called coefficients of friction. Both mu's are the coefficients of friction. And their values will typically be between 0 and 1, although it is possible to get super sticky tires, for example, that have mu values as high as 1.4 or 1.5. And you can think of the mu value as being like a percentage of the normal force. So for example, if mu is equal to 0.3, let's say it's a mu sub k, then what we're saying is that the kinetic frictional force will be 0.3 times whatever the normal force is, or in other words, it will be 30% of the normal force. Over here, with our static friction and the inequality, what we're saying is that the static frictional force will grow until it hits the max, and the max is exactly mu sub s times the normal force. And once it hits that max, then it can no longer hold the object in place, and the object now begins to move, and as soon as it begins to move, then it transitions over into kinetic friction. The values for mu sub k are always less than the values, or maybe equal to, less than or equal to the values for mu sub s. And you can find different values for mu sub s and mu sub k in two different places. First of all, there is a link that I put onto Edmodo that links to an entire table of kinetic and static frictional coefficients. And the second place that you can find them is in a chart in your book. And if you look in your book on page 90 in section 4.8, then you can find a small chart of coefficients of static friction and kinetic friction. Interestingly, the chart in the book says that you can get a coefficient of static friction as high as 4 with rubber on other solid surfaces. So there you go. All right. Well, that's the theory. Now the question is, what else can we say about these, and how do we solve problems with them? Well, if we go back to creating a static and kinetic frictional force chart here, what we know so far is that static is for objects that are not in motion when v is equal to 0, and we know that the static frictional force is less than a max, which is mu s times the normal force. Kinetic frictional force applies when the velocity is not 0, and the kinetic frictional force has a constant value, which is mu k times the normal force. All right, well, we can say a little bit more about this. Let's take a look at an object that is experiencing a static frictional force. Maybe it's got some applied force this way, and it's got a weight, and it's got a normal force, and maybe it has a different applied force F2, like this, and that applied force is going to have components that are vertical and horizontal, just like that. And now comes our static frictional force, just like that. Because the velocity is 0, and because that does not change until the object breaks free, that means that the acceleration is going to be 0 as well. Not only is the velocity 0, but until we hit the max, the acceleration will be 0 as well, because the velocity is not changing. And so that means that in the horizontal direction, when I add up forces in the x direction, then F and F2 are both horizontal forces pointing to the right, and they are positive, and Fs is going to be pointing in the opposite direction, and therefore it's going to add up to zero. All of those have to add up to 0. I'm using Newton's first law because our acceleration is 0. So that when I solve, what I see is that Fs is equal to, excuse me, I should have F2. Okay. What I see is that Fs is equal to the sum of all of the other forces. In other words, it is an equilibrium force that cancels out all of the other forces in its direction. So this gives us a direct equation that we can use to solve for Fs. If I were to generalize it, I would say that Fs is equal to the sum of the other forces in its direction. By contrast, the kinetic frictional force is going to be in operation when v is not equal to 0, and it may or may not be the case that the acceleration is equal to 0 for any given problem. We would have to watch the motion to be sure. And we have this single value right here. But what is the case is that Fk will always take the direction that is opposite to the velocity. So if I have a free body diagram that looks like this, with weight pulling down and normal force pushing up, and I have only the kinetic frictional force acting, then looking at this, I can immediately tell the velocity is going the other way because the kinetic frictional force is always opposite to the velocity. Notice that the velocity does not go as a force on my object here. It's not one of my red arrows because velocity is not a force. But it is okay to draw it off to the side, just showing what direction it's acting. Or you can do it down here, and that'd be cool too. Just so it's clear that it's not a force. All right, so what we have now is a good idea of the circumstances under which we use static and kinetic. We use static when the velocity is 0, kinetic when the velocity is not 0. We have a good idea of how to calculate the static and kinetic frictional forces. The static frictional force will be the force that is needed to cancel out all the other forces. The kinetic frictional force will be equal to mu times the normal. And we also have a good idea about when we transition from one to the other. As soon as my static frictional force gets to be equal to mu s times Fn, which is the max, then the object will transition over to the other type of friction. And we also have a good idea of direction. The static frictional force will be in whatever direction is needed to cancel out the other forces. The kinetic frictional force will be opposite the velocity. All right, with all of that in mind, let's work a problem. Let's take a 20 kilogram block and set it on a table. And the coefficient of static friction between the block and the table we're going to set at 0.6. Please notice that some problems will tell you the value of mu directly. This is one such problem. And other problems will give you information to figure out the value of mu. So we're going to see one of each here. So we have the object on the tabletop, and I'm just going to rewrite my us equals 0.6. And there's going to be an applied force. We'll call that F. And the question is now, what value of F will cause the block to move. Okay, so we're going to begin with a free body diagram. Let's see what we have. We have a 20 kilogram block. We're going to have its weight pulling down. I'm going to label that as mg is 200. We're going to have a normal force pushing back up. We have the applied force, which has a value of F, and we are going to have a static frictional force pushing back. How did I know that I would have a static frictional force pushing back? First of all, I knew there would be a frictional force because they gave me a coefficient of friction, which implies that the table is not frictionless or smooth. Second of all, I knew that it would be static because the block is currently at rest. We're looking for the value that will cause the block to move. And also, a confirming clue was that the mu I was given was mu sub s. And then the third thing is the direction. I knew that the static frictional force would point this way because the only other horizontal force acting on this object is pushing to the right. So, that's our free body diagram. Now we're going to analyze it with the horizontal and vertical components separated. So we do the sum of forces in the x direction and the sum of forces in the y direction. Let's do the y direction first because that's more familiar to you. We have Fn pointing up, and we have mg, which is 200 newtons, pulling down. And the sum of forces in this direction is going to be 0 because the block is not accelerating in the vertical direction. It's sitting there on the table. And that immediately allows us to solve Fn is equal to 200 newtons. Then, the sum of forces in the x direction is going to take into account all the horizontal arrows. So we have F, which is pushing to the right, and we have Fs, which is pushing to the left. Now, is this a Newton 1 or a Newton 2 situation? In our situation, we are looking for the value of F that will cause the block to move. The block is currently not moving, and until I hit that max force, it will not change in its motion either. That means its acceleration is 0, and this is a Newton 1 situation. We're going to set those forces equal to 0. So this allows me to figure out that, adding Fs to both sides, that the force that is needed to make the block move is going to be when Fs is at its maximum. And the maximum value for Fs is mu times the normal, and we are given mu, and we are given the normal force of 200 newtons. And so this tells me that the force needed to make the block move is going to be 120. In other words, I come along and I push on the block, and if I start pushing with a force of 0, I will increase that force until it hits 120, and right at that moment, the block will break free. So the only thing that we added here was we added the fact that the static frictional force maximum value is mu times the normal. Now let's consider the same block once it has gotten moving. So here's our 20 kilogram block again. And we are now going to subject it to a force of 40 newtons. And that force of 40 newtons is not enough to get it moving, but it is enough to cause it to move with constant speed. Let's call it constant velocity. And so we want to know now what is the value of mu k. Alright, so this is the scenario we're given. We're pushing on the 20 kilogram block with a 40 Newton force, and we observe that it moves with constant velocity when we do that. So what is the value of mu k? So again, we do free body diagram, 20 with the weight of 200 newtons pulling down, and normal pushing back up, 40 newtons pushing this way, and just looking at these forces, it seems pretty obvious that the constant velocity we're talking about is going to be to the right. And that means that my frictional force, Fk, is pointing to the left, opposite the direction of the velocity. Now, we're ready for sum of forces in the x direction and in the y direction. And for the sum of forces in the x direction, we take all of the horizontal arrows. Oops, I got the signs wrong now. 40 to the right and Fk to the left. Will this be a Newton 1 or Newton 2 situation? Because we have constant velocity, that means the acceleration is 0, and therefore my sum of forces is also 0 in the x direction. Likewise, my sum of forces is 0 in the y direction because my block is not accelerating up or down vertically. And so I can immediately solve both of these equations to find that the force of friction is equal to 40 newtons, and the normal force is equal to 200 newtons. And I'm happy with myself, but for one thing, I'm looking for the value of the use of k. And I say, yes, I remember. The force of kinetic friction is equal to mu k times the normal, and I have both of these values. And therefore, dividing both sides, I get mu k is equal to 0.20. Notice that because the value of mu k is smaller than the value of mu sub s that we computed over here, right there, that was given to us, that means that it takes less of a force to keep a block moving than it does to get it moving. In other words, if I took a look at the same kind of force diagram that we had from our demo, it takes 120 newtons of force to get the block moving, but as soon as I do get it moving, then the amount of force to keep it moving drops to a mere 40 newtons. Well, I hope